Hello, everyone. My name is Ian Tracy. I am going to be presenting on software availability protection in cyber-physical systems. This was a paper presented in August of 2025 at the Usenix Security Symposium in Seattle, Washington. The two main authors of this paper are A.O. Lee and Jinwei Wang, and a third author is Ning Zhang. All three are from the Computer Security and Privacy Laboratory in Washington University in St. Louis. And at the bottom, you can find a link to view the entire paper. So what we're going to get into in this presentation, we're going to start off with a little motivation. What's the reason for this research? We're going to introduce the research and some of the people behind it. And we're going to talk about the contributions this research had to the field of security. We're going to talk about the actual CPS platforms and hardwares that this solution was able to run on. And then we're going to have a problem formulation where we're going to define the actual problem. We're going to talk about different assumptions and what the threat is modeled as. Then we're going to get into the details of design and how it was implemented. Finally, we're going to talk about evaluation criteria and then the results in conclusion. The paper starts with the authors characterizing the overall software protection market. They think that most software solutions focus on detection and address availability as a less critical feature. There are many efforts that improve system resiliency. However, they are limited by a specific fault model. They tend to recover crashes due to a specific fault. One example is concurrency bugs, but they're not generally suited for cyber attacks, which tend to be more adaptable. And solutions offering recovery is often focused on data, either by rebooting or reloading snapshots, and not particularly focused on peripheral configurations or the state of peripheral machines. The motivation behind this research is that most software protection projects focus on detecting violations of confidentiality and integrity. However, little work has been done to preserve availability after a detection. While this might be acceptable in IT scenarios, this is certainly not acceptable for cyber physical systems, especially real-time safety critical systems. So the authors created Gecko to bridge this gap. It's an attack recovery approach with two main features. It timely recovers execution after an attack, and then it uses compartmentalization to selectively disable exploited features. This project was named after a gecko, a creature that has a remarkable ability to sacrifice particular limbs in order to save itself. There are several contributions that this paper made to the field of cybersecurity for cyber-physical systems. It created a criteria for measuring real-time software availability and recovery, two metrics, one they call liveness and the other they call timeliness. They created Gecko, a set of recovery techniques to achieve real-time software availability, where repeated exploitations are thwarted by replacing exploited features in the system with fail-safe ones. Gecko also has a novel approach to considering peripherals and the state of peripherals that interconnect cyber and physical components. And then they implement a prototype of Gecko and evaluate it on 3 real-world cyber-physical systems, assessing its feasibility in normal execution and attack scenarios, and analyze the factors impacting its performance. This paper covers a lot of current approaches for resiliency and recovering from faults. And you can see here in this nice chart, they summarize whether the attack scenario is designed for general programming, kernel drivers, or cyber-physical systems. Many of the models for the attack are simply faults, not necessarily cyber attacks. And they extend metrics for timeliness and liveliness, as well as focusing on if these mitigations require hardware modifications or can be done with controller redesigns. And I'll spend a little bit of time to summarize the notes. So the approaches for execution continuity are execution environment manipulation. This identifies faults and modifies the external environmental conditions that led to that particular crash. The limitation they noted was that these faults are really limited to interleaving of threads, and these faults must be known ahead of time, and it's not well suited for just addressing general attacks. Malicious input filtering uses dynamic tracing to detect and filter malicious inputs during an attack. This approach has an expensive runtime overhead. Nversion relies on multiple implementation versions as a form of redundancy. Crash resilient instruction set introduces unique memory instructions that trigger a handler upon a security violation, which requires a new hardware set. For recovery, there is systems that implement a system program restart. They simply reboot the system or the program when they detect some sort of intrusion. However, they noted that rebooting the Jackal UGV took around 87.3 seconds, so it's quite violates the timeliness requirement. Micro reboot restarts just a single component. While they noted that this wasn't an advanced technique and had better timeliness results, it was still really difficult to make real-time guarantees on a system where one or more components could be restarted. Re-execution, this approach recovers the program by re-executing from a previous programming point, which didn't work well with stateful operation, which many cyber-physical systems have some sort of state involved. And the same went for checkpoint restore, where sometimes it can take considerable time to restore operations for peripheral devices, and also does not work well for stateful operations. The first real-world CPS platform that Gecko was assessed on is ArduPilot, which is an open source software project for unmanned vehicles running on an unmanned aerial vehicle. ArduPilot claims to be the most advanced, full-featured, and reliable open source autopilot software available. This software is capable of controlling almost any vehicle system imaginable, from conventional airplanes, quadplanes, multi-rotors, and helicopters to rovers, boats, balance bots, and even submarines. The second real-world CPS platform is Jackal, an unmanned ground vehicle, a UGV, which is a ruggedized, weatherproof research robot. It runs ROS on an x86 PC. Another test platform for Gecko was the Open Manipulator X, which is an open source robotic arm equipped with the industrial grade software stack called MoveIt. It's based on a Raspberry Pi 3B for compute. Included a Pi camera module V2 and inertial measurement units on each joint for capturing motion data. This paper provided formal definitions to the problems that it addresses. It defines real-time software availability as the ability of a task or process to meet deadlines in real-time cyber-physical systems. And the two metrics for recovery timeliness is the system's availability to recover from a single attack within a known period that can still allow for the system to maintain safety. In many contexts, timeliness is defined by service deadlines, but the authors highlighted that in cyber physical systems, it's really necessary to maintain the safety of the system. And liveness is a system is considered to be live if it is capable of eventually completing execution. And the authors noted the differentiation between typical systems where liveness is recovering from a fault. In cyber-physical systems under attack, typically the attack can be repeated. So it's not just one-time recovery but the ability to endure a repeated attack. This paper and the Gecko project makes some assumptions about the threat model and security goals, and I'll cover them here. They assume that a CPS program contains one or more remotely exploitable vulnerability. They assume there is a threat detection monitor in place. This monitors violations of security policies. The security goal is real-time availability, and that the defender will regain control with the degraded feature set in a timely manner to preserve the operation under persistent attacks. They assume that the hardware, OS hypervisor, and Gecko components are secure. They also assume that the software source code is available so that they can add instrumentation code. And really, they're focused on addressing memory corruption attacks of user space applications. So they consider out of scope hardware attacks, sensor attacks, and side channel attacks. I'm going to introduce a technique here that is widely used throughout the project, which may be new to some people. So I want to give at least a brief introduction prior to explaining how Gecko was designed and implemented, and that is instrumenting code with an LLVM pass. This is going to be widely used throughout the project, like I said, and it's going to be used to add compartmentalization and track references. It's an interesting technique in that it really doesn't modify the source code. The essential idea is at compile time, you're going to find places in the code that you really care about that are interesting, and then you're able to add instructions to that code around those interesting places. So this works on an LLVM intermediate representation. This is low-level code, maybe between the source code and the machine code. And if you're really interested in how exactly this works, I can recommend CS6340 Software Analysis. This course gets really involved in writing these LLVM instrument passes. And indeed, the majority of the course is doing just that. Mostly focused on software reliability and robustness and picking up certain bugs, not particularly security, but you can see here the techniques are applied to security. The key idea behind the design of Gecko is to leverage feature reduction upon recovery to ensure system availability. And while feature reduction might sound like something that is not able to be tolerated by these systems, fault tolerance is already a safety and CPS design requirement. There's two examples highlighted in the paper where fault tolerance is actually a requirement for these systems. The two examples are EN 50128, which is a railway standard, and ECSSQ HB6002 Alpha, which is a European Space Agency software requirement. And indeed, the authors noted that in all four CPS platforms, they already included some semblance of fault tolerance. Gecko classifies faults into two categories: transient. These are simple faults that can be resolved with a restart, and permanent, ones that are not resolved by a restart and require some sort of replacement or feature redundancy. And they classify redundancy as either identical replicas or what they use, which is feature degraded replicas with fail-safe modes. And they really embrace this idea of simplicity as a fallback in order to control complex system. And that idea is to transition to a simpler and safer controller when faults are detected in complex controller code. I'm going to walk you through a high-level flow of how Gecko works, going from left to right. At compile time, Gecko adds instrumentation to implement compartmentalization and recovery. During runtime, Gecko enforces protection, detects attacks, and identifies the attack surfaces. When Gecko realizes a compartment is attacked, that compartment is isolated, reducing the attack surface. It also transitions to a reduced feature recovery block, and this will prevent runtime delays. And then the last step is selective recovery rolls the corrupted program state back to a clean one and resumes execution. A Gecko compartment is an isolated code region along with its accessible data, peripherals, and allowed control flow transfers. The idea is each instruction belongs to one compartment, but data and peripherals can belong to many compartments. And compartments are defined by a policy, and the default compartmentalization policy is to organize them by tasks. The partitioning of compartments is conducted on a program-dependent graph. This is an iterative process that begins partitioning each component from the entry function of each task. It performs forward analysis and groups all the related code and data. When this forward analysis reaches code or data belonging to a different compartment, it indicates that these elements are not exclusive but are shared among different compartments. Gecko removes them into a separate compartment and grants access to the related compartments. Concretely, data shared by multiple compartments are grouped into global compartments, and compartment stacks are allocated to separate regions to prevent cross-stack corruption via the stack pointer. The actual implementation of compartmentalization utilized an open source project called ACES. Gecko employs an LLVM front-end analysis pass to identify compartment transitions, global data access, and cross-stack memory interaction between compartments. Each source file containing a task from the task list forms a compartment. At linking time, a Python script is used to separate the code and data of the same compartment into different ELF sections and place them in contiguous memory address space. Enforcement comes via the trampoline code that is instrumented for indirect jumps and write instruction targets within a compartment. This adds a reference monitor to access the global variable compartment and other compartments. Runtime dependency between compartments is constructed by recording all global data access and inter-compartment calls. Gecko's attack detector monitors for violations of the expected security policy at runtime. When an attack is detected, Gecko traces back to the compartments that received the malicious input based on runtime dependencies. The identified compartments will then be isolated so that the entry points of the attack are removed. Gecko leverages this runtime context to attribute the detected attack from the compartment where it was identified to the compartment that received the malicious input. For the implementation, Gecko uses the built-in control flow integrity, or CFI, from the LLVM compiler. CFI is a system that tracks which functions are allowed to call targets or control flow addresses. It also uses value-based data flow integrity, or DFI, derived from a project called OAT, to detect DFI violations. When an original compartment is disabled, the shadow compartment swaps in and handles invocations from other components. These inputs are categorized as either non-essential or essential for making control and performance. Non-essential inputs, such as user interface inputs, primarily affect operability, while essential inputs, such as sensor data, are critical for control performance. Gecko provides two modes for handling these inputs within the shadow compartment. The default mode ensures execution of continuity for non-essential inputs. You can think of this as kind of hard code default values or default functions for non-essential data flows. While the customized mode handles reductions in essential inputs, the aim here is to achieve graceful degradation of performance. This is done via the dedicated recovery blocks. And developing such a recovery block is typically requires domain and application specific knowledge. The authors state that it is challenging, if not impossible, to determine when a malicious payload enters the system without significant state recording. Programs that periodically save checkpoints can very well do this after the attack has occurred. Thus, Gecko ensures that checkpoints are made just after system initialization, before any attack could occur. The attacker can also tamper with the memory write operations used to configure sensors and actuators. While rebooting can initialize these peripherals, it takes a considerable amount of time for reconfiguration. Gecko leverages built-in compartmentalization to prevent malicious sensor and actuator configurations at runtime. Gecko partitions the function calls for configuring sensors and actuators as separate compartments at compile time, and then at runtime, Gecko ensures that sensor compartments will only allow reconfigurations that are specifically permitted through a whitelist according to the security policy. The performance of Gecko was evaluated under 3 simple criteria. What is the runtime cost of running Gecko under a no attack condition? How effective is Gecko at recovering from an attack? And does Gecko work on real cyber physical systems? So the results for the evaluation criteria of changing the runtime cost under no attack or normal conditions, you can see, well, the highlights are that they tested this over 100 runs, and the runtime overhead for real-time tasks, just simply measuring task execution for ArduPilot, which had 30 tasks. You can see here in the diagram at the bottom, where each task, they show the different percentiles at the bottom of the execution times. The baseline on the left, the blue, is without instrumentation of Gecko, and the green on the right is with Gecko. The takeaways, the results are an 8.26 increase to the execution time, which came with a 4.7 increase to the standard deviation. The authors thought that this increase to the standard deviation, this variation, was due to cache misses introduced by the instrumentation code. And for Jackal, which had 8 tasks, a 7.52% increase to the execution time and a marginal increase to standard deviation. One important thing to note is they did not find any violations of real-time task deadlines. And the memory overhead for running Gecko under no attack conditions were 184.2 megabytes for Jackal of the 16 gigabytes that were available. And for ArduPilot, 10.8 megabytes of the 1 gigabyte available. So in order to test the effectiveness of Gecko under attack, the authors needed to emulate an attack. They noted that the most prevalent memory vulnerabilities that they could attack are out-of-bounds writes, use after freeze, and OS command injections. And they chose to use out-of-bound writes, saying that they're similar in response to these other type of vulnerabilities. So for ArduPilot, they injected a vulnerability into its user interface component based on the real-world CVE, which is for ArduPilot. It wasn't clear to me in reading this and researching it if when they said they injected it, if they created a new one because it was already patched, or if they actually used the branch that the CVE highlighted. And then for Jackal, just because it's a little bit newer, they weren't actually able to find real-world CVEs for that project, and they injected a vulnerability based on user inputs. So these attacks were randomly triggered after a random duration of runtime. For Jackal, this was an out-of-bounds write on the actuation signals, altering the throttle value sent to the actuators, and then to emulate repeated attacks, the attack was reactivated at random intervals between 0 and 1 seconds after the initial activation. The author's criteria for determining the effectiveness of Gecko for recovering from attack was measuring software availability by meeting task deadlines under these attack conditions. This is measured from the time of attack to when the program resumes execution after restoring its state. And when they say that deadline hit means making the deadline. If you exceed the deadline, it's a miss. So they averaged this over 10 runs. The recovery time was 15.1 milliseconds for ArduPilot, and the results were that 4 tasks out of the 39 missed deadlines, which is an 87.9% hit rate. And for Jackal, the results were 35.4 milliseconds with one task out of 6 missing deadlines on average. And that's a 83.3% hit rate. Comparing this to some other techniques where a complete device reboot typically has a 0% hit rate, and then simply restarting the program, but not the actual complete device, was a 2.6% hit rate for ArduPilot and 16.7% hit rate for Jackal. Another criteria for determining the effectiveness of Gecko at recovering from attack was measuring the deviation between an actual trajectory and a reference trajectory over time. Under normal conditions, when there are no attacks, Jackal deviates about 0.03 meters from its reference path, and ArduPilot deviates 0.12 meters. And during an attack, Jackal only deviated 0.51 meters, where ArduPilot deviated 39.98 meters. So to determine if Gecko actually works on a real-world CPS system, they had a case study focusing specifically on the Open Manipulator robot arm. This robot arm was programmed to execute a predefined mission emulating an industrial workflow, which would detect the position of a box by recognizing a QR code. It would grab the box and then place it at a designated location. To emulate an attack, a buffer overflow vulnerability was intentionally added to a function that processed user input. And so without the attack on any given run, the max force on any joint would be 120 newtons. But under the attack, during the buffer overflow attack, they found a spike of about 200 newtons. And the author said that this caused the robot to slam into the table. And so with Gecko, that was prevented during the run. With Gecko, Gecko detected the illegal write operations and prevented them. It then disabled the compartment responsible for processing user input. And then since this compartment did not handle any essential data or code for ARM control, the deactivation only affected the operability, and the ARM defaulted to moving back to its initial position. Subsequently, the software rolled back to its initial state, which takes about 8.71 milliseconds. To evaluate the impact of Gecko under normal conditions, they measured the performance overhead. It showed that Gecko introduced a runtime overhead of 7.97% and a memory overhead of 61.4 megabytes. But despite these overheads, the authors noted that the system successfully ensured that all real-time deadlines were met. Wrapping up the conclusions from this research, it provided formal definitions for real-time software availability and defined two concepts or parameters, or properties called liveness and timeliness. It proposed a solution to achieve those, which was Gecko, which had the features of vector identification, selective disable of exploited features, compartmentalization of code, selective reset of program state. The authors noted there were a couple limitations or areas for additional research. One was inconsistent recovery based on initial checkpoint restore. They noted that CPS systems inherently have state or need state to perform. And so always defaulting back to the initial state was somewhat of a limitation. And then limited shadow compartment implementations. So they only had two different modes, default and a custom, but further research, further domain expertise in creating these safe fallback compartments would greatly improve performance.